What I want to talk about is an example of some of the ways that I think technology can be used. Primarily, I see opportunities, significant opportunities, of simplifying some intellectual processes in order to access big ideas. And we've heard one or two examples being talked about. I mean, something like calculus. One of the things I find depressing is to see kids leaving secondary school with good grades in mathematics, but if you talk to them about calculus and start talking about rates of change, that they don't seem to really know what you're talking about. And that seems to me to be a mismatch in some places. But I think there are potentially enormous impacts on the group who are not going to go on and do A-level maths, but who are going to go into the world of work. There's potential for hugely improving engagement with some of those young people. But one of the things that I think we need to be a little bit cautious about is that sometimes if we do this, the kids will not recognize that they're doing mathematics at all. And let me try and explain that a little bit, because it sounds perverse almost. But there was some work done a number of years ago now about mathematics, the nature of mathematics in the workplace. And the researchers, Celia Hoyles and Richard Noss is here, discovered that I see a very high proportion of the mathematics that they could see being done. The people doing it didn't think that they were doing mathematics. They weren't reporting it as mathematics because they were using computers to do it. So I think that there are some significant opportunities for using computers to do a lot of mathematics, but by embedding it contextually and improving access, I think we can do things about changing perceptions of mathematics in doing that. And I'm going to look particularly at things to do with data as maybe the most pervasive area of mathematics that people will come across. But it's not. The principles are not just to do with mathematics. So we're going to look at a social sciences example to start with. If you look at differences in educational achievement, but in an awful lot of social sciences, you're looking at inequalities of one sort or another and trying to explain what's going on, but very often without the background of the data. Because if you overlay patterns of achievement by different ways of categorizing, whether that's gender, ethnicity, social class, you don't get the whole story. So let's have a look at the sort of graphs that people would see in social sciences. You can look at differences between boys and girls, differences between those who are eligible for free school meals or not, differences between ethnic groups, and sometimes they'll be treated to a comparative bar chart, so you can make a double comparison. But you can move a bit further, and this social science teachers might say, well, there's a new report has come out from the Commission on Equality and Human Rights. And this graph shows boys and girls and whether they're eligible for free school meals for the ethnic subgroups. But would you really want to take that into your classroom and start to try and make sense of it? And more than that, I would argue that this graph actually encourages you to make inappropriate comparisons because it's only showing you all of the ethnic subgroups. So you're encouraged almost to compare white ethnic subgroups with Asian ethnic subgroups with black, and you can't make other level comparisons. What about being able to explore the data for yourself? And part of the difficulty has been that data is too complicated for people to explore using tables or using static graphs. But we would argue that interactive data displays actually let you access things by simplifying the processes of understanding the data. And hopefully, I'll be able to So this is the same data that you saw earlier. But it's now making the comparisons at the higher level. So these are the main ethnic groups rather than the subgroups. But if I look at these tabs up at the top, I can actually drill down and I can make the same sorts of comparisons for the subgroups within any of those main ethnic groups. Now that's the same comparative bar chart that I showed you before, but the difference here is that in the slider, I can disaggregate that and I can now look at just the group who are not eligible for free school meals, and I can look at the group who are eligible for free school meals, and I can make some comparisons about what is going on with it. Now, this seems to be accessible to kids who are not good at mathematics, have no background in mathematics, but they don't see it as mathematics. They're not being asked to do any calculations. They're not being asked to do any actual graph drawing, but what they are seeing is the information that is pertinent to the subject, the core subject, that they are going to be asked to produce explanations for. And as a starting point for accessing that sort of information, and then looking for the explanations. But the other sort of thing that I can do with this is that I can interchange the position of those variables. So I'm now making the direct comparison for the different ethnic groups between the groups who are eligible for free school meals and who are not. And again, I can disaggregate by looking just at the boys and the girls. I'm not going to take a long time to display the rest of that, but there's more information that's in here. One of the things that I found when I was teaching in school was that at age 12, 13, 14, you got this maths is boring kicking in, and you had kids who were interested in changing the world and kids who were good at mathematics, and they almost seemed to split into non-overlapping universes, where in mathematics they never met any data that was of any interest in terms of saving the world, changing the world. The social sciences had lots and lots of words, but never seemed to get the impression that mathematics was a useful tool for them. Those are the sorts of things that are in the mathematics curriculum. But it's not just things like social sciences. There are lots of physical sciences examples as well. So there's an example of oxygen production and photosynthesis, where you get important ideas, nonlinear relationships, piecewise behavior, and so on. And I can look at the relationships that are in there, and I can see I get things like optimization, but I also have the opportunity to make the model a little bit more complicated because I can introduce more variables. So I've got not just temperature and light intensity, but I've also got carbon dioxide levels there. One of the things that I would like to see in the way mathematics develops is more use of this sort of thing. There are opportunities using things like data loggers to collect multiple simultaneous readings of different variables that can then be fed in. And we're starting to explore ways of working with a reach-out lab in Imperial College, where you might get multiple groups of kids doing experiments and then contributing those results to larger databases so they can do their own analysis the way they would always do, but that they can contribute to larger databases like this, but for things like carbon emissions. How do we take carbon dioxide out of industrial emissions? Those sorts of things open up possibilities for getting kids to actually see and engage with real science and the mathematics that pervades all of that.